the first part.
Mm-hmm. Okay, that's the radius relationship. We know that the acceleration of object in the radial direction can be written this way. So what's very interesting from here is that we multiply r dot. That's what will give us a dot squared, and then we integrate.
Oh, what is little m here?
Little m is the mass element.
Okay.
Yeah. So we'll do an integral on dt maybe. On the left hand side, that simply becomes dr. And then we can divide r squared everywhere, and maybe also multiply. So multiply -2 and divide by r squared. Becomes r dot squared over r squared equals 2 gm over r cubed. c over r squared. And because
Is it minus 2c, or it's just a constant?
yeah, it's just a constant. It doesn't matter. Because r equals ARS,
Yeah.
so we have a dot over a squared, and then our mass is 4 over 3 pi r cubed rho over r cubed. So we see that becomes 8 over 3 g pi rho minus some kc squared rs squared a squared. So a1 is 8 over 3 g times pi. Okay?
Mm-hmm.
So in the second step, we need to um, treat mass energy as the same. Okay, we will treat this relativistically. So basically, mass is energy, energy is mass. And to do that, we use the first law. That's the problem said. We need to use first law, and we need to treat it as a adiabatic system. Because it's adiabatic, it's just dW. And that pressure, the work from that pressure is PdV. So we'll just use related rates from here. The total energy is mass times speed of light squared. And the volume is 4 over 3 pi r cubed. And of course the mass is density 4 over 3 pi r cubed c squared equals negative p 4 pi r squared dr. On the left we need to do a chain rule. Rho 4 over 3 pi r cubed c squared plus rho 4 over 3 pi r cubed c squared 3r squared dr. All that equals negative p 4 pi r squared dr.
What else did you differentiate? Because you split it up into two terms, but
Uh,
one of them doesn't have a differential.
Rho is a quantity. Yes, rho t, you see? Rho is a function. That's a function of time.
Don't you have to take a derivative of it in the first term?
Yes, I should. So I should write rho prime.
Okay.
Mm-hmm.
And that's with respect to time.
Maybe I should, no, I should write d rho. I should write d rho, yeah. Otherwise, I should just write a rho dot. Okay, so let's divide by. I think we all have a pi somewhere.
Yeah, I think
Um,
fourth is pi r squared.
hmm. No, I think I have way too many r here. Um, yeah, I have way too many r here. 3. Hmm. So maybe divide by 4 pi r squared everywhere. Yeah, divide by 4 pi r squared everywhere. Rho dot 1/3 c r c squared. Rho c squared equals negative p dr r dot. So we'll just use r dot at this point. So in order to make it look like that, we need to divide by 1/3 rc squared everywhere. And also combine the leg terms. Hmm. Okay. Yeah. So A2 will be 3. Okay. Let's continue looking. Okay, so that's where Hubble's parameter comes in. It's also the Hubble constant.
Wait, they're saying that
Mm.
for the case of the photon, as the universe is expanding, the photon's wavelength expands proportionally to the scale factor.
Mm.
What does that mean, really?
It means the wavelengths of the. It means the wavelengths of light corresponding to those photons
Will also
becomes
expand.
bigger. Yeah, becomes bigger.
Okay.
So
So all distances get scaled.
that's right, and those light becomes less energetic.
doesn't make sense from like a particle point of view.
I guess it doesn't. It's just it, yeah, it's just losing energy because it's expanding. You know, the energy density is decreasing. You only have so much energy in that space, and that space is becoming bigger. So I think we need to use the previous equation. Try to make some space here. So I think we need to use that equation if it's only light, then it will be made of these many light particles, and their wavelength is becoming bigger. And we also know that P over C squared is rho, W rho. So that's actually a general result. 3h1 plus W equals negative rho dot over rho. If we integrate this, Rho is some rho naught maybe, e to the negative 3h 1 plus w t.
Do we have to use the fact that that wavelength change fact, because earlier in the problem they mentioned one of the terms of the first equation can be interpreted as energy density?
Yeah. So now we can find that energy density. Joules per meter cubed. um, so this will be proportional to a to the negative 4. Oh, I realized we cannot stay as h here. We cannot stay as h up here. We better rewrite this, because h is a over a dot over a. So really we have another one, ln of a. So rho is some rho naught a to the negative. There's still a 3. And no t either. Right? Okay, so now we can see this is negative 4. So how can this be negative 4? W must be 1 over 3, yeah.
Can you explain how you got that it's proportional to a over 4? So you get the r cubed contributes 3 of those, and is the f the last one?
Yeah, from the wavelengths.
Okay.
Yeah. So that's where that information is used.
Okay.
Volume contributes r to the 3, and wavelength contributes r. Okay, so what if it's non-relativistic matter? Then the energy will simply be m naught c squared rest mass. Okay, rest mass energy over v. So this will simply be a to the negative 3, and w will be 0. Finally, constant energy density. Oh, so that's just a to the 0. Therefore, w will be negative 1.
So is that, they asked this because it's transitioning, how the universe might transition, right? So from the radiation to then the cooling down, and then perhaps it'll become constant energy density far into the future or something like that.
Yeah.
three.
Uh, 3 would be steady, steady universe. It doesn't expand or contract anymore.
Mm-hmm.
So let's see if there's anything that will match up here. Okay, is that Q? Yeah, I think Q is W here. Okay, Q equals 0 is the non no acceleration universe. So observation shows we are actually pretty much constant energy density. Actually, pretty much constant energy density. Dark energy is rho CW squared. W less than 1/3 for cosmic acceleration. This leads to a positive value A double dot. Okay. Constant energy density. Uh, okay. Well, very interesting. This question really has some interesting physics packed into it. So 3 is constant energy density due to a lot of dark energy.
Mm-hmm.
Dark energy. But we don't know where that dark energy comes from. So let's keep going. Um, in the case k equals 0, so we need to go back and look at that formula. Um, A rho h squared equals a rho minus that.
So the second term is just gone.
So h squared equals a1 rho. But rho is, we just derived. Rho is rho, some rho naught a to the negative 3 1 plus w. And that is a dot over a, which we need to take a square root. So it becomes, let's call that just some constant b, which is root a1 rho naught. So a dot, well, a dot times a negative 3 over 2 1 plus w minus 1 equals some constant. Integrate a naught from a. Uh, Pretty messy expression here.
You have to use the case, the condition A0 equals 1 though.
Oh, so here
For,
I cannot. Okay, maybe it's better not to be too general. at this point. So here for photons, W is 1/3. I would get 2/3. -1, -2. Oh, that's a positive. W is -1. Okay. So the so the last one is exponential expansion.
Oh yeah, so I have a question. So there's like, isn't there like three different ways the universe could
Uh-huh.
evolve, and one of them is like the crunch, I think it's called, like it just collapses.
Uh-huh.
Another one is just nothing goes, doesn't go either way, it doesn't go infinite expansion, it doesn't go crunching, so it just stay it kind of, I guess the acceleration goes to zero or something. And the last one is like the huge expansion. So
Uh-huh.
like do these three represent, because these three represent
The
different
the
things.
lar- the last one is the huge expansion you're talking about.
Yeah,
It's exponential.
but the rest are still increase.
The other two solutions are also expanding. All three solutions are expanding. Um,
So what kind of solution would, how would you get a big crunch?
a big crunch. A big crunch would mean um, a negative acceleration. And that is when, that's weird. I would imagine that's when that there is enough gravitational acceleration to pull it back, right?
Yeah.
I mean, physically that makes sense. If you have a lot of matter, the gravitational influence would pull it back. In fact, I believe that's some conclusions they arrived at. There is a minimum energy or mass density that's needed for that to occur. So, in terms of these solutions, I mean that's when a double dot becomes negative. But a double dot isn't a double dot always negative? Hmm. But how can this be negative? Our starting equation is that being negative. Okay, but that's classical. In the relativistic version, in the relativistic version, we have seen how rho acts as a function of radius. So I would say this is the neutral, maybe the neutral state. This has to be neutral. That's right, that's the zero. That's when the total mass is conserved. There is no increase or decrease in mass. A dot is a constant. A double dot is zero.
Yeah.
Okay. A dot. A dot. A dot. Is A dot a constant? How do we know A dot is a constant in this case? We have to rely on this version.
And the second term should be a 0.
Yeah, for uh, for A dot to be 0, rho dot has to be 0, right?
Yeah.
Wait, doesn't that mean A rho is constant? Rho doesn't change over time? I think this equation is not exactly that. Wait a second. Yes?
Yeah.
Okay, but that's their Q. I think maybe their Q is not our W.
Actually, I see that they've used W, our W, in a similar context. At the top of the page you're right on, it says, we can then rewrite the Hubble parameter as this huge square root. And you see they actually use W in the exponent of uh, that.
Mm,
So
mm,
they
mm.
have a different W, unless two different people wrote this article.
Energy density. Okay. I'm just trying to see if Q can be linked to W. I have this equation up here. Missing a 3. Well, there now, certainly this makes sense using their notation. Q equals 0.
Mm-hmm.
Yeah, if Q equals 0, then A double dot is necessarily 0. A dot is a constant. So I don't think so. From here, I don't think Q is W. Q is not W. Um, there is another article. Okay, so that is W. Negative pressure. Repulsive action. Okay, interesting. So it behaves differently from normal matter. If Q is less than -1, then it will expand. If Q is less than -1, it will expand. Same here. But they seem to be slightly different. QO. Big rip. Big rip. Okay, that makes a little more sense now. Okay, maybe we should let's see if we can read the next one. Let's see if we can finish this part. Spatial +1 positive curvature k equals 0 flat negative curvature critical energy. Okay. Okay, so we need to copy that first equation again, which is this one. Express k in terms of omega, which is rho over rho c h, so that's h squared a1 rho minus kc squared rs squared a squared. Omega is rho over rho c, and rho c is h squared over a1 c squared. So rho a1 c squared over h squared. So if we divide by h squared, get 1 rho a1 h squared. And also divide by c squared. over c to the fourth minus h squared. H squared r squared c squared. I don't feel this is right. My units are not right.
I have an extra a squared multiplied to the whole thing.
I'm I'm worried omega is no omega is a dimensionless number. How can I have over c squared? Omega is a dimensionless number. So what just happened here? Rho c is that c squared is on top. Why do I have this rho a1 over h squared? What is going on?
For your 1 equals rho a1 over h squared, the second term has to have a squared in the denominator, right?
Do I must have a squared? I divided h squared. I divided h squared.
But the original denominator of the second term has a r squared a squared.
Yeah, but that's just r squared. Because because rs time a is r. But something is not right.
Yeah.
Omega over c squared. I am dividing everything by c squared, h squared, r squared. You see, that can already not be right. That cannot be right because I have a 1 here. That's dimensionless. I should just have omega here. That's really weird. My omega is a dimensionless number. A1 c squared. That's a dimensionless number. Oh, because that's A1 rho. So I must have omega h squared. No, but I'm dividing h squared. That's all messed up. That's yeah, I feel like I should just redo this. Something is not right. So if I just come back to this, I have h squared equal to a rho minus kc squared over r squared. A1 rho. That's my omega. So I will just write omega h squared over c squared. Wait a second. Something is not right. Omega is dimensionless. Or unless it's not, really. Uh, okay, h is dimensionless. No, h is per second squared.
Mm-hmm.
H squared is per second squared. What's A1? A1 is G pi. G pi. Newton meter squared per kg squared. What is this? The right hand side is joules per meter cubed. Okay, I don't agree with that equation. It's impossible. That's not possible. Something they messed up something.
Mm-hmm.
That's joules per meter cubed. That is not joules per meter cubed. A row. A row. Unless did I copy my A1 correctly? Okay, what's the unit for A?
Same as G, just same as capital G.
Uh, okay. But up here, that row is kilogram per meter cubed, right? So 1 per second squared Newton meter squared per kg squared times kg per meter cubed. Newton meters is kg meters squared per second squared times meters. So that one is okay. That one is okay. That one is okay. Therefore, there is no way this can work. Unless that's not energy density. That's that's joules per meter cubed.
Oh, I see what they said.
Uh,
Rho C squared is the critical energy density. So
Joules per
rho
meter
C,
cubed.
so rho C is
Uh,
still
1 per second squared. Because because if you do this over A1, if you do this over A1, that is the same as kg per meter cubed.
hmm So maybe they just meant.
That's not joules per meter cubed.
Hmm
Uh, anyway, that's weird. I feel they shouldn't have added c squared. Then it would be okay.
Yeah.
Then it would be correct. I think there's a problem with this formula here. The dimensions do not work out. This is still total energy. total energy density. This is still joule per meter cubed. So that is kilogram per meter cubed. Kilogram per meter cubed. And that's joule per meter cubed, which cannot be right.
Yeah.
And this one, this is unfortunate. International Physics Olympiad. Something is not right. Okay. All right. We'll stop here today, and we'll work around that. We'll work around that. So that's why you should always check units. It
Mm-hmm.
really just tells you what has happened. In your calculation. Okay.
Yeah. Thank you.
Have a good night. Bye bye.
Bye.